The Topos Institute Colloquium. Today, we are pleased and honored to have Eugenio Moggi from the University of Genova, who will be speaking to us about categories of classes for collection monads. So for our viewers on Zoom during the talk, please feel free to unmute yourself and interrupt if you have any questions. There will be short breaks in the talk where you can ask your questions. So Eugenio, whenever you're ready.
Okay, thank you very much for this opportunity. As I said to you, I don't have a paper related to this presentation, but I will be happy to share the slides and send them to you. Hopefully, I will have something by the end of the year submitted. So, okay, so let me start with some motivations. So the motivations are the use of monads for modeling collection types in the context of database languages. There is some work by Buneman and others. And a paper by Ernest Mannes, where he identified a class of monads on set that are suitable for modeling collection types, because not all monads on set are that appropriate. Okay, so, and the goal of this presentation is to generalize the idea in this paper by Mannes so that we can replace set with some other category that is more suitable in the context of database languages, in particular categories where arrows correspond to functions that can be computed in polynomial type or anyway low complexity. So in the presentation, I will first of all recall the results in this paper, then replace the category of sets with the category of countable sets. Observe that this category is a model for category of classes, which is basically the counterpart of Bernays set theory in the category-theoretic framework. And I will use ideas from this category of classes to develop some sort of realizability models that provide these categories that should be suitable for databases and where we can have a notion of collection monad in the sense of Ernest Mannes. Okay, so first of all, I recall some facts about the category of sets. So in the category of sets, all monads preserve monos. This allows us to define a notion of support for an element in M of X. So we say that P, a subset of X, is a support for C if C belongs to M of P, which is necessarily a subset of M of X. With this notion of support, we can define when a monad is finitary, namely every C in M of X has a finite support. Please notice that the support, it may not exist the smallest support, but it's enough that there is one that is finite. Then there is a well-known result by Lovier that in set finitary monads correspond to algebraic theories. Now there are two categories, full subcategory of sets, the category of finite sets, that's a topos without a natural number object, and there is the category of countable sets, that's not a topos, but it's an example of category of classes. And the topos inside this category is just the topos of finite sets. Now, a first restriction on finitary monads is to require that finitary monads restrict to countable sets. This is, in terms of algebraic theory, this corresponds to require that the signature omega is countable, is at most countable. Okay. So now I will introduce the two equivalent definition of collection monads proposed by Ernest Mannes. The first characterization is equational. So a finitary monad, or better, a collection monad is just the monad, the finitary monad, induced by a particular type of algebraic theories that are called balanced. This means that all the equations in the theory are such that the terms on the left and the right-hand side have exactly the same set of free variables. So this is very simple equational characterization of collection monad. The other one, which is the one that I will be able to generalize to other categories, is that collection monad is just any monad on set for which there is a taut monad map to a particular monad, which is the finite power set monad. Now, I will then recall what it means taut in this context. But before, let me give you some example of finitary monads that are collection monads. So, of course, there is the finite power set monad, the list monad, or the binary tree monad. So these are all, if you think in terms of equational theories, you see that they are all balanced equations. An example of a monad, finitary monad, which is not a collection monad, is the monad for groups, because you have the equation where x multiplied with the inverse of x is equal to 1, so it's not balanced. Actually, this is not a proof that it's not a collection monad, because there might be other equational presentations that are balanced. So it's, but trust me, okay. So now let's explain what it means taut in this context. So the notion of taut is defined for functors and natural transformation, and therefore it can be generalized to monads by requiring that the functor and the natural transformation that are part of the monad have this property of being taut. And the definition makes sense not just in the category of sets, but in any category where you have, let's say, finite limits. That's enough. Actually, what you need is just inverse image, so pullbacks of monos along arbitrary maps. So a functor is taut if it preserves these inverse images, okay? And a natural transformation between functors that are not necessarily taut is taut if for every mono you have that this naturality square is a pullback. So in this case, we don't necessarily have that Fm and Gm are monos. But of course, if F and G are taut functors, these are also monos. Okay. A general fact is that if you have a taut natural transformation from a functor to a taut functor, then also F must be taut. Okay? So in particular, if we go back to this definition, if we have that P of F, the finite power set, is a taut monad, then of course, any monad that has this taut monad map is necessarily taut. Okay. Now, the main point will be, okay, we have this finite power set monad. Is there some way, alternative way of recovering it rather than taking it as out of the hat? Yes, there is a way, and the way is to adopt the ideas developed by by Joyal and Moerdijk when they introduced this category of classes. So the idea is that you have you start with a category with certain properties. In our case, would be the category of countable sets, and the object in this category correspond to classes, and so we need a notion of small, which allows to define what it means to be for a class to be a set. However, we are interested in small maps, which are families of sets indexed by a class. So we need this additional structure, this class of small maps, which of course it's a subcategory of C. And in the case of set omega, the obvious choice of small maps are the maps such that each fiber is finite. So we have a family of finite sets. And now we can recover the finite powerset functor as a classifier of small maps, or sorry, of small relations. I will explain later what is a classifier for small relation, but first let me define what is a small relation. So a relation is small if, by composing it with the first projection, we get a small map. Okay? So in particular, in the case of set omega, small relations, and with this particular choice of small map, small relations are finitely branching relations. So for every x, there are only finitely many y's related to x. Okay. So now, so once we have this notion of small relation, we can define what is a small relation classifier. A small relation classifier is a small relation. Here, this is membership in the other direction, such that this functor that goes from our category C of classes to sets is representable by this object here. So for every small relation from x to y, we have there is a bijection with the maps in C from x to what is called power object of y. Now, when we have this power object or power class object, if you are interested in modeling Gödel-Bernays set theory, you look for initial algebras for this functor. Okay, and that would be like the von Neumann universe. Of course, I'm not so much interested in set theory. I'm interested in this kind of object, this small relation classifier that in the case of set omega correspond to the finite power set monad. Okay. Oh, so now let's see what is the plan to start. So I've introduced the results by Bernays on collection monads in sets. I've shown that we can restrict to countable sets. Now I'd like to move to some category that it's a bit more suitable for database languages than the category of countable sets. So the idea is then to replace in the work that people have done on the category of classes, to replace the assumption on C. Usually the assumption is that it's a hating pretopos which means that it's a category with finite limits, well-behaved sums, so it's extensive. It has quotients of equivalence relation, and it has, well, existential quantification and universal quantification. So we have logic, a sort of first-order logic. I will be happy to replace this requirement on C with just the extensive categories. So just finite limits and well-behaved sums. As far as the small map are concerned, usually the property of small maps require the category C to be at least a regular category. So we have well-behaved images. But again, I want to have something that makes sense in a wider context. So I want to have axioms for these small maps that are expressible just in the extensive categories. And actually what I will do is to, since this power object, which is the classifier of small relations, needs a notion of small relation, I could jump directly to a definition of small relation and skip small maps. Okay? So, if there are any questions, I can stop here. And then I will start on how to get other categories in place of set omega. Okay, if there are no questions, let me summarize some issues that I want to address. So for database languages, we want to have types with decidable equality and a very simple Boolean logic. The work by Bernays says that this finite power set monad is the mother of all collection modes, at least in set. And what I want to do is to replace this with another collection monad that will be the mother of all collection monads in whatever category you prefer to use for database languages. And the other important point is that in algebraic set theory, if you want, in category of classes, this power set monad can be recovered from a notion of small relation. Okay. Then the plan is to look for the extensive categories, so finite limits and well-behaved sums. A class of display maps. By class of display map, I mean a subcategory of C. So it is closed by composition. It has all the identities, and every small map can be pulled back along any map in C. In particular, what will happen is that all most classes of display map that I will consider have a classifier, which means that there is a small map such that all the others can be obtained by pulling it back along suitable arrows. Now, in extensive categories, there are several classes of display map that I can consider. There are decidable monos, so they are classified by the injection of 1 into 2. There are regular monos, and of course there are all monos. These are all classes of display map. Since C is as finite limit, also C is a class of display map. And another class is the class of split epis. So epis for which there is a partial inverse. Now, I want to look for this C and some S, and here I have some display map available on C for free. So what I expect is that whatever notion of small map I will use, it should include at least the decidable monos. Okay. Now let's focus, go back to the category of set omega, of countable sets. So it is extensive. It has a subobject classifier, and all monos are decidable in this particular category. It's a locus in the sense that it has a parameterized list object, and in particular, it has a natural number object. It's a pretopos, so it's much more than extensive. We have axiom of choice, so we have that all APs split, but of course, this is not what in general should happen. There is an obvious choice of small map classifier. Since we have a natural number object, we can take just this map that for each natural number n give us the set of its predecessors, which is finite, and that's the obvious choice of small map classifier. So we have this. And then we have several closure properties that maybe I'm not so much interested in spelling out. And now what I want to do is to replace set omega with some other category that will be included in set omega, but will include the category of finite sets. And the way to get these categories is to use or adapt realizability. Realizability usually is defined in terms of applicative structures like partial combinatorial algebras or model of the lambda calculus. What I will do instead is to replace these applicative structures with a monoid of functions on some set of data. So the idea is that we have some set of data and some subset of the function from D to D that we consider computable. So this is very much in the spirit of a paper by Dana Scott on relating theories of the lambda calculus, where he described category theory as a sort of theory of functions that is milk and water and is based on composition rather than application. So if you just have a monoid, you don't get very much, but you can add requirement on this monoid, and then you can start getting something more interesting. Okay. Now, if we have this monoid, I can define several categories by analogy with what people do with realizability. So let me, well, of course, if I have a monoid, I can consider the category obtained by splitting the idempotent. That's a bit more interesting than the monoid itself. Another category is called the category of assemblies. Let me describe it briefly. So the objects are a set and a relation, which for every x in the set says what are the element of what are the data that represent that particular element of the set. So this relation should be a surjective relation. So every x has at least one D representing it. And arrows are just set theoretic functions that are for which there is a computable function that transforms a representation of x into a representation of f of x. Now, I'm mainly interested in this particular full subcategory of assemblies. which is described here. So they are the assemblies for such that for every X, there is a unique representation in D. Or if you prefer, you can say that it's the category of subsets of D or predicates of D. Okay. Of course, all these categories, if I take just some monoids C, well, they don't have very interesting properties. However, if I start to assume that C satisfies some additional properties, in particular, these three properties, namely, all constants, constant functions are in C. And I also require that there is at least two elements in my set of data. Then I have a way of encoding pairs. So I have an encoding of pairs in D such that I can extract using a map in C from the encoding of a pair its component. And if I have two computable maps, so F0 and F1 are in C, by doing this pairing, I get again a map in C. So in particular, with this property, I can conclude that the idempotent, the category of idempotent, has finite products. And then the third property is to have a quality test. So I have a map in C that modulo the encoding of pairs, which of course allow me to encode any tuple. I can test, given 4 elements, I can test if the first two are equal, and if they're equal, I return x2, otherwise I return x3. Okay. Now, if C satisfies these 3 properties, then what do we have? We have that these categories are extensive. Of course, also the category of finite set and the category of set are extensive. And all these functors, so these functors are full and faithful, and this is just faithful, they preserve the extensive structure, so finite limits and sums. And this gamma is just the global section functor, defined in this way. Okay, so now we have a lot of ways of producing extensive categories, and I'm mainly interested in this one. Let me introduce some other extensive categories, at least extensive when C satisfies these 3 properties. So one, again, I'm mainly interested in subset of D. So in particular, I can consider the full subcategory of predicate on C, where the predicates are decidable. What does it mean, decidable? Well, since this category is extensive, it means that the object here should have a map. The object here are correspond to maps from D, which I can view as an object in this category, to the object of the Booleans. Since it's extensive, we have this object. Okay. Okay. Under this assumption, actually, what happens is that this category of decidable subobject of D correspond with the splitting of idempotent plus the initial object. So it's very simple category. And of course, in all these categories, since they are extensive, I have this class of display maps that are available in any extensive category. Okay, and now I'm ready to define what I mean by a small relation in any of these categories in this diagram here. So I just leverage on the notion of small relation in set. So a small relation in any of this category is a decidable relation. So it must be a decidable mono, this one. And if I apply the global section functor, I should get a small relation in set, namely what I described as a finitely branching relation. Okay? Okay, now I will give you some examples of monoids that satisfy this property. Well, I will just mention them, and then I will focus on just one, namely the monoid of polytime computable functions. So let's go in order. So first, let's start with, let's take D to be the natural numbers. If we take as C the set of all functions of natural numbers, well, what happens is that this category of decidable predicates coincide with the category of all predicates on D, sorry, and this is just set omega. More interesting monoids are the monoid of primitive recursive maps. Okay, so in this case, we don't have that this equivalence is no longer old. We have that decidable subobject are strictly less than subobject of n of the natural numbers. In this category here of decidable subobject using primitive recursive maps, I have a natural number object. But now if I take a smaller monoid, in particular here I consider a subrecursive monoid, like the one of Kalmar elementary maps, which is strictly contained in primitive recursive maps, then I no longer have a natural number object in this category. Now, I just recall what is a Kalmar elementary map. It's a map that can be described by this expression interpreted in the set of natural numbers. So I have summation, product, bounded summation, bounded product. This is testing for equality. So it looks very much like Martin-Lev type theory, but in arithmetic form. Okay? The other example that I want to consider, they are not examples of monoid on natural numbers, but on bit words. So here, instead of natural number, I take strings of bits. And therefore, I can use notions like from complexity theory. So I can consider the category of linear time computable maps, linear or more precisely modulo constants, and using, of course, multi-type Turing machines, or polytime computable maps, again, on using multi-type Turing machines. By the way, if I start with a combinatory algebra, I can recover a monoid by considering the functions that are expressible using an element of the combinatory algebra. These satisfy these two properties, but they don't satisfy the third property So there is no testing of equality. Okay. Now I will focus just on the case when C is the monoid of a polytime computable map on bit string. Now, the properties that are given in this slide, they are just general ones, so it's not specific for this particular monoid, and it's just a recap of what I've already said in previous slides. Okay? So if you missed something, that's a sort of summary. So I consider just these two particular categories, so the category of predicates over D and the category of decidable predicates over D. So they are all extensive, so we have all these classes of display map. They are well pointed in the sense that the global section functor into set is faithful. And moreover, this functor is extensive. In particular, this means that decidable subobjects are mapped into subobject in set. So it's faithful also on decidable subobject. If I consider just the category of decidable predicates on D, then we have that this category that I just referenced C, it has an object, namely D, and every X is a decidable subobject of this object. And moreover, this category is equivalent to the category that I obtained by splitting the idempotent on D, viewed as an object of C, plus the initial object. Okay? Okay, so these are general properties that in particular hold if C is the monoid of polytime computable map on bit strings. In the next slide, I will consider other properties that hold for this monoid P of polytime computable maps, but fail for linear time computable maps. Okay. So for this particular monoid P, we have a taut strong map. So this means that all that this functor is taut, the eta and mu of the monad are taut, and also the strength of the monad, which is a natural transformation of this type, has to be taut. We have also a taut natural transformation that gives us a small relation classifier. But now I have to define what is a small relation in one of these categories. Okay? So I leverage on the fact that I have this global section functor. So I could say that a relation in C is a small relation if it is a decidable object in C, and if I take its image in set using the global section functor, I get a small relation in set, namely a finitely branching relation. Okay? Probably there is a cleaner way of getting this without relying on this global section functor, but we have it, so let's use it. And the other important thing is that this taut natural transformation is a small relation classifier for small relation in C. It's not just that, we have some other important property that sort of capture the notion of support introduced by Bernays in the category of sets. Okay? So namely what we have that for every map in C, where C is one of these two categories, from X to this power object, there is the smallest small relation such that this map here, composed with the tensorial strength, factor through this small relation, sorry, P of this small relation, in a unique way because this is mono. Okay? And actually this smallest small relation that has this property is obtained simply by pulling back this small relation classifier along this map obtained from G. Okay? Now, I didn't say what are small maps. I only defined what are small relations, but if you are interested in going into the framework of category of classes, the small maps will be obtained by composing a small relation with a projection. Okay? Okay, now I could stop here, but actually there is some dirty work that I have to do, because here I have claimed some facts without proof, and in order to prove all these facts, I need to move to bit manipulation and consider algorithm on bit strings to show that all these facts that correspond to existence of certain polytime computable functions actually work. So let me show some steps of this dirty part of a proof, which is normal when you use realizability. So for every X, so decidable subobject of D, I have to define what is this other decidable subobject. So what I do to define this is to use some encoding of sequences of D in D. I introduce an extra symbol so that I can split. Okay? So if I have a sequence of bit string, I can use this symbol to separate one bit string from the next. I can take the concatenation of all this in this bigger alphabet, and now I can encode this alphabet into 2 bits and therefore go down to bit strings. So I have a way of encoding sequences of bit strings into 1 bit string. And moreover, the size of the encoding it's given by is linear in the size of the encoded sequences. Second thing that I need, it's a linear order on D that should be easy to compute. Of course, the obvious definition of linear order between bit string is to say that U is less than V if it's shorter, or if it's equal, is the same length, but in lexicographic order comes before V. this predicate, it's easy to decide because it's linear time decidable. So certainly polytime. And now to define this object, decidable subobject of D, what I can do is to represent finite subsets of D using a sequence of element, or better, the encoding of a sequence of element of D that are in increasing order. And of course, since all this encoding and this testing for whether the linear order odds are easy to compute, they are polytime, I can show that this relation, it's polytime, so it's a decidable object. Okay, once I have defined this encoding of the finite power set of X, then the rest is quite easy. It's easy to show that the unit which will map so what I have to prove here is that given a bit string representing an element in X, I should be able to use the bit string representing the singleton. So I just use a list containing only the element of D that represent the element of X. With mu, it's a bit more complicated, but also this one, it's easy to compute in linear time. Okay, so actually what I have to do is to do some merging of sorted sequences and then some pruning to remove copies, because I want to have something in strict linear order. I have to show that if G is polytime computable, also this, which is the action the functor P applied to G is polytime computable. Also, this requires some dirty work, but it's quite easy. And finally, I have to prove that the tensorial strength is polytime computable. This is actually quite easy, because what we do is basically to map let's see. Yeah, I have to map. Here there is something missing. Yeah, I guess. Yeah, there is something missing here, but I have an element of D that represents the element of X. I have the encoding of a sequence of element of D that represents this finite subset. And of course, here I have to produce a sequence which are obtained by pairing. So each element of the sequence is obtained by pairing the element U, representing an element of X, with each element of the sequence, the I, representing this sequence of element in Y. Okay. And then, of course, I have also to show that this inclusion is polytime computable, but that's, again, quite easy. Okay? Okay, so this is the dirty work. So let me, I'm almost finished. So let me summarize. So if you know some axioms in this category of classes, in particular, there is a paper by Awodi and others in this archive, I think. Let's see, where is it? Yeah. Annals of Pure and Applied Logic. Yeah. You can see what kind of properties you lose when you move from this monoid, where basically you get set omega, and you go down and up to linear time computable maps. So when you get there, you no longer have this small map classifier. So P is somehow the limit, probably. When you go above, you get more interesting properties. But only here you get the full properties that you expect from a category of classes. Okay, so I'll stop here and I will take questions.
Thank you, Eugenio. Thank you. So, for questions, there are two ways of asking questions here. You can either raise your hand and then I will call on you and you can ask your question. Or if you are not able to unmute yourself, you can type your question in the chat and I can ask on your behalf. Okay. Any questions for Eugenio? I have a question, Eugenio. So you mentioned that there was relationship to databases in your work. Can you perhaps like say a little bit about that? How you know, how does some of the results here influence our design of databases or design of algorithms on databases?
Actually, the appropriate reference for databases is this paper by Buneman and others on bulk types. And if you look at them, of course, they don't use collection monads. They are just assuming that we have a monad, but then they start asking some additional properties, like the fact that equality of collection should be decidable, and therefore also equality on the data that you put in the collection should be decidable. Okay, so when you say decidable, of course, what do we mean? From a logician point of view, it means that it's Turing decidable. Mm-hmm. From a database point of view, you require that it's decidable in low complexity. And usually low complexity in the context of databases is polytime, maybe even lower than polytime, but polytime is as far as they are prepared to go. So if we go back to this point, made here, the database point of view comes when you insist that the category that you are working with has a Boolean logic. So the Boolean corresponds to the extensive structure, so it's 1 + 1, is not some subobject classifier. And all objects must have a equality that is classified by this Boolean, not the normal subobject classifier. And of course, there is no way in category theory to say that something, an arrow is polytime computable. So you have to use categories that under the carpet use only polytime computable algorithms. Okay?
Thank you, Eugenio. Okay, we have some questions in the chat, so I'll read them out. So Mikhail asked if you could share a link to archive or presentation. So I think you mentioned at the beginning of your talk that you would be putting a paper on archives sometime later this year.
I'm afraid it will be end of the year, but
End
I'm
of the year.
happy to share the slides. So I will send you the
Yes.
slides, and you can put it. I don't know if you have a web page.
Yeah, we have a Topos Colloquium website,
Okay.
so we will put your slides on the website. Thank you.
And I will fix whatever was missing in one of the slides.
Thank you. Marty asked the following question. In some situations, one might want to consider probabilistic maps that are computable in polynomial time. Can the methodology here capture that situation as well?
I don't know. So the point is the choice of monoid here. What do you mean? So let's say I take bit strings as the if you are able to provide a notion of function on bit string that it's computable in this probabilistic way, then you can check whether this monoid satisfies this property, and then there is some dirty work to do, like the one that I did for the monoid of polytime computable maps. But I'm afraid I cannot answer because I don't know exactly what would be this monoid, but that's the strategy that I would suggest. If you have some other choice of, if you have your preferred choice of computable maps, say.
Okay, thank you. So dirty work here refers to proving that something is computable in polynomial time, moving outside of the to actual some actual analytic proof or combinatorial proof.
Sorry, can you repeat?
No. I was just making a comment about your word dirty work. I like that you use that when you're talking about proving the polynomial time properties of the maps. Okay, so Kevin has a question. He asked, how far does this monoid-based approach to realizability go? I may well have missed it, but can you construct realizability toposes this way, as well as the weaker structures that you're focusing on? It seems very attractive.
Yes. So here I've stick to monoid of total maps. Of course, if you consider partial combinatorial algebras, this setting is not suitable because you have to consider partial map as well. But for example, if you consider combinatorial algebras or model of the lambda calculus, then any combinatorial algebra induces a monoid that satisfies two of these three properties. But even if you don't have this equality testing, if you have a monoid induced by combinatorial algebra, you have enough to get much more than the extensive category. You basically recover the notion. So let me go back here. You recover the notion of assembly that is used starting from a combinatorial algebra. And actually, there was some, let me go to the references. There is a paper by John Longley in mathematical structure in computer science, where he introduced an even more general notion of realizability than the one I used, where instead of monoid of maps, he consider relations, and instead of just one data type, he has several data types. So you have a typed relational structure for defining computation. So if you want something general as possible, I suggest this paper by John Longley.
Okay, thank you very much for that. And we have one more question on chat, and I also see that we have a hand raised. So I'll ask the question on the chat. So ABC asked, generally in computer implementations of category theory in the category of sets, the available packages such as Algebraic Julia focus on finite sets. So in summary of your talk, do you mean that it is possible to formalize and compute with more complicated sets than finite sets? Can you remind us which one explicitly?
Yes, so the sets that I consider, okay, so let me, yeah, so let's focus just on this category here. So let's D be some, be the set of bit strings, then the kind, so, sorry, actually it's better to move to this one, decidable subset. So what does it mean, decidable subset? If you say, if you take polytime computable maps as your computable maps, the object in this category are the polytime decidable subsets of bit strings. Okay, so you can operate on these sets because I mean, you have something to decide whether a bit string belongs to this set, and that's what I suggest to do.
Okay, thank you very much. So I think we'll take one last question. And Maria, I think you have a question. You can unmute yourself.
Yes, thank you very much for your talk. I would like to know if you can present these results in terms by using Lovier doctrines. Because, for example, the category of predicate is the Grothendieck of the doctrine of predicates. So you will have to have some doctrine of decidable predicates and with a specific structure, like a Boolean algebra, something like that. So I was wondering whether you can present this and relate it to free completions or.
Okay, I could certainly present it in terms of doctrines, because all this category of display maps, they certainly, or at least the one where you have monos, they can be formulated as doctrines. Regarding free completion, I'm not so sure. But let's say this category of decidable subobjects is very much related to this work of you on arithmetic universes in Colloquium categories. So in that case, you will have to use the monoid of primitive recursive maps to have a Colloquium category, but yes, it would fit in this framework. And it's somehow more general because you can go below primitive recursive maps.
And sorry, another question. What is your final goal?
My final goal was to replace set with some complexity-aware categories and still be able to define this notion of collection monad as defined by Bernays. So he only introduced this notion in the category of sets. What I've shown is that somehow you can generalize it to other categories, and basically it turned out to be the finite power set monad in disguise.
Thank you.
Okay, thank you. Now I'm going to end the live stream on YouTube, and we will continue our discussions on Zoom.
Okay.
Okay, so the live stream is, I've ended the live stream, and please